In our last lecture, we were examining the modeling and control of an anti-aircraft gun. We were examining how picking the controller gain affected the transient response of the gun to a step input. We know that common performance metrics for transient behavior, like rise time, settling time, and percent overshoot, are dependent upon pole location. So we're very much interested in how pole location is related to the controller gain for this example. Recall that we found the closed-loop transfer function of the system had a second-order denominator. The poles of the closed-loop system are the roots of the denominator polynomial, the roots of s squared plus 8s plus kc equals 0. So kc determines these roots. Kc determines the poles of the closed-loop system. If kc is greater than 0, then these poles will be in the left half plane, and the closed-loop system will be stable. Where the poles are in the left half plane is determined by kc. If kc is between 0 and 16, the poles will be on the real axis and distinct. If kc is equal to 16, the poles will be on the real axis, but will be repeated at -4. If kc is greater than 16, the poles will be complex conjugates. They will have a non-zero real and imaginary part. Please recall that the modes will depend upon the pole location, and since the pole location depends upon the value of the controller gain kc, we can affect the modes of the system through the choice of the controller gain. Consider the case where kc is less than 16. Then we have two poles on the real axis. Each of these poles will have a time constant. The one closest to the origin will have the larger time constant. It will be at -1 over t1. The one that's farther away will be at -1 over t2. These two poles will be arranged symmetrically about -4 on the real axis. Mode number 1 will be the slow mode. It will decay slower because its time constant is larger. The second mode, with the pole at -1 over t2, is referred to as the fast mode. It's the fast mode because its time constant, t2, is much less than the time constant of mode 1, which is t1. Now let's look at the case where kc is greater than 16. In this case, we'll have two complex conjugate poles. We'll mark their real axis location as -1 over t, where t is the time constant of these poles. And their imaginary axis location will be plus and minus j omega d, where omega d is the damped natural frequency. For these two poles, we'll have complex modes. The complex modes will be sines and cosines times a damped exponential. The damped exponential term will be e to the minus t divided by capital T, the time constant. Of course, that decay is dictated by the real part of the complex poles. Now, recall that the pole location will depend upon the controller gain kc, and so by changing kc, we can affect which complex modes happen to occur. Let's now evaluate the closed-loop behavior in a more quantitative fashion. We know the poles are the roots of the polynomial s squared plus 8s plus kc equals 0. If we compare this to the standard second-order form that we have for transfer functions, the denominator there is s squared plus 2 zeta omega n s plus omega n squared. So clearly, omega n here is equal to the square root of kc. And then we can find the damping factor. Zeta is equal to 4 over square root of kc. So we see the controller gain kc affects both omega n and zeta. Assuming that we've picked kc so that the poles are complex conjugate pair, we'll find now the time constant of the system. Recall that the time constant is 1 over zeta omega n. Since zeta omega n is equal to 4, we find the time constant is 1/4 of a second. The settling time can then be found as 4 times the time constant. So the settling time for this system is 1 second. Note that here we're using the simple formula for settling time, that settling time is 4 times the time constant. I want you to note that the time constant here is independent of the value of kc. This is because the real part of the poles does not change as kc is changed, provided that the poles are complex. So if the poles are underdamped, the time constant will not change as kc changes. And under the rule that the settling time is 4 times the time constant, the settling time will also not change with kc. That's because kc does not affect the real part of the poles. Since the settling time is actually dependent on the value of zeta and not only on the value of the time constant, the value of kc chosen will in fact affect the settling time. So if we've chosen kc to be greater than 16, we may want to choose a particular value so as to reduce the settling time, even if we cannot actually change the time constant. Let's now examine what happens if kc is less than 16 and the system is overdamped. If kc is less than 16, the poles will be on the real axis, and they'll be symmetric, about -4. In this case, the pole with the larger time constant will dictate the transient behavior. That is, the pole that's closer to the origin on the real axis. For ours, this was at -1 over t1, and the other pole was at -1 over t2. So our settling time will be approximately 4 times t1. Since this pole is closer to the origin than -4, the settling time associated with this pole will be greater than 1 second, and therefore it's desirable to pick kc greater than 16 so that the system is not overdamped. As designers of the control system, we're interested in how percent overshoot, rise time, and settling time will vary with kc if kc is greater than 16. That is, if our closed-loop poles are underdamped. As kc increases, the poles will move away from the real axis on the vertical dashed line shown, and in the direction of the red arrows. The real part of the poles will remain unchanged, but the imaginary part, omega d, will increase. As the poles move in this fashion with larger values of kc, we'll see changes both to omega d and also to zeta. Zeta will decrease as kc increases, since zeta is equal to 4 over the square root of kc. As zeta decreases, the percent overshoot will increase. So larger values of kc will result in larger values of percent overshoot. With zeta greater than 0.6, the percent overshoot will be small. It will be less than 10%. So this is a desirable range of values for zeta. If zeta is chosen between 0.77 and 0.87, then the settling time will be less than 4 times the time constant. To see this, we need to refer back to the graph that we saw in the previous presentation. It showed there's a region of zeta between 0.77 and 0.87 where the settling time was less than 4 times the time constant. So this is a desirable region for us to pick zeta in if we're going to pick zeta to be greater than 0.6 so as to achieve small overshoot. In this case, the settling time will be less than 1 second. Let's now look at how to pick zeta so as to achieve a quick rise time. And you'll remember the relationship between rise time, zeta, and omega n was a bit more complex. To simplify the analysis, we'll look at an approximation of this relationship that's good for large values of zeta. We'll simply fit the curve with a line. So we'll find that the rise time times omega n equals 5.5 times zeta minus 2.1. And this is a good fit for zeta greater than 0.65. Recall that omega n was the square root of kc, and that zeta was 4 over the square root of kc. We'll plug these two values into the equation that we just had on the previous page in order to find the rise time as a function of kc. And after a little bit of algebra, we'll find that the rise time is equal to 22 over kc minus 2.1 over the square root of kc. So this allows us to try to pick kc so as to make the rise time as small as possible. Of course, we want to pick kc such that zeta is between 0.77 and 0.87. The range of kc values for the region of zeta values that we're interested in corresponds to kc between 21 and 27. So we'll now plot the rise time as a function of kc over this range. And what we'll find is the rise time decreases with increasing values of kc. This example problem was to illustrate the relationship between the controller gain kc and the various specifications that's achieved by the closed-loop system. We weren't given precise specifications in order to design our controller. But let's suppose that we desire to have the percent overshoot less than 10%, the settling time less than 1 second, and we wish to minimize the rise time. In this case, the best value of kc to choose would be 27, because this achieves the minimum rise time while having the percent overshoot less than 10% and the settling time less than 1 second. So you've now seen how the transient response of a system can be tailored via feedback control, how we can achieve a desired percent overshoot, rise time, and settling time, and how we can think about the design process from the point of view of locating the closed-loop poles.